In this particular video we're looking at galvanic cells. Galvanic cells are the basic chemistry behind all of the batteries that we use nowadays. If you put a chunk of zinc, a bit of zinc metal, into a solution of copper sulfate, what happens is the actual zinc gets this lining across the whole surface, not just around the edges as shown in this diagram, gets a very thin layer of copper being deposited on it. That's because when a copper ion, and you also need to think in terms of this is a copper sulfate solution, so the copper ions and the sulfate ions are dissociated, they're ionized, they are separated. Anyway, when a copper ion bumps into the surface of the zinc, it steals 2 electrons. It literally takes 2 electrons, it's very attractive to electrons, or more attractive than the zinc, and 2 electrons from the zinc metal pop into a copper ion which is bumped into the surface. That means that when the copper ion grabs 2 electrons, it turns into a solid copper atom, and that is deposited on the surface. At the same time, because the zinc has donated 2 electrons, a zinc atom turns into a zinc ion, and the zinc ion goes into the solution. Now eventually over time, the piece of zinc, the zinc electrode, actually gets smaller because it is turning into zinc ions which float around in the solution. At the same time, the blue copper sulfate solution gets less blue because the copper ions, which give the solution its colour, are deposited as copper atoms on the surface of the zinc electrode. Overall, the equation is represented here. I've got solid zinc plus copper sulfate. It's going to give zinc sulfate solution and solid copper. We can set up almost exactly the same idea, but have the zinc and the copper sulfate separated. So they've been popped into 2 different beakers, and we've got a copper electrode in this case, and a zinc electrode, and a voltmeter, and we've got something called a salt bridge, which we will explain shortly. So what happens is a copper ion bumps into the surface of this copper electrode. It is so attractive it pulls electrons from the zinc. Okay, so I get a flow of electrons flowing through from the zinc through the voltmeter into the copper. Okay, so electrons are attracted onto the copper ion, and effectively it sucks electrons all the way through. So a piece of the zinc metal turns into a zinc ion, as we saw previously, and turns into a zinc ion. So that a piece of zinc metal zinc atoms turns into a zinc ion in solution, and a copper ion in solution turns into a copper atom. Now again, this is equivalent to what we were just previously looking, but it is separated so that the electrons have to travel through an external circuit. And if we've got electrons travelling through an external circuit, that is a flow of electricity. Okay, so we've got zinc turning into a zinc ion, we've got a copper ion turning into a copper atom. These are all the parts of a galvanic cell. So we have a cathode, we have an anode, we have a salt bridge, and we've got our electrolytes down the bottom here. Now, in terms of this, let's have a look at what's happening. The zinc once again is turning into zinc ions. Therefore we've got 2 electrons flowing through into a copper ion which bumps into the surface of the electrode. The cathode is where reduction occurs. So I just remember it as red cat. Reduction occurs at the cathode. And here's the reduction equation. So I've got copper ions being reduced, they're gaining 2 electrons to form solid copper. So red cat reduction occurs at the cathode, and the cathode is given a positive charge. Think of it in terms of the electrons are attracted towards the positive, the negatives are attracted towards the positives. At the zinc electrode is called the anode in this case because it is losing electrons, it is being oxidized, and oxidation occurs at the anode. And here's the equation for the oxidation of zinc, solid zinc, which is our anode, into zinc ions which go into solution, and the electrons. Now it's those electrons that then travel through the external circuit. We need to talk about the salt bridge now. The salt bridge allows the continual flow of negative charge around the circuit. So in this case I've got electrons flowing through the external circuit. Now I've got sulfate ions in here which are negative. They start flowing into the salt bridge. The salt bridge, in this case it's potassium nitrate. Those sulfates repel the nitrate ions in the salt bridge, and the nitrate ions in the salt bridge travel into the left hand half cell. Now this constitutes a flow of negative charge all the way around the circuit. They complete the circuit. So the movement of negative ions through the salt bridge completes the circuit. The salt bridge also stops the cells becoming polarized, which means that it stops them becoming charged. Now if we think in terms of our copper sulfate solution here, some of these copper ions, are coming out of solution. They're turning into solid copper. When they do that, that reduces the number of positive ions in the solution, which means I've got a net balance of negative ions in here. Those negative ions, in fact in this case sulfate ions, repel each other and start repelling each other up through here. So their movement through here effectively equalises this charge, because I'm getting rid of positives and their flow through here is getting rid of the negatives. In the same case here, on the left hand side, the zinc metal is turning into zinc ions. Now those zinc ions are in solution and they're positively charged. That means I'm getting extra positive charges in here. That also means that the negatives coming through here, being pushed through here, balance out the extra positives in there. It just means that the actual half cells, and each one of these is called a half cell, doesn't get an overall charge. The continual flow of ions through the salt bridge means that I don't get a build-up of positives in here because the negatives come through and balance, and I don't get a balance of negatives in here because the sulfates are moving through. If you withdraw the salt bridge, you literally just remove it, the galvanic cell immediately ceases to work. The standard hydrogen electrode involves an inert electrode, for example platinum, and then we've got a test tube here through which is pumped some hydrogen gas, and I have got hydrogen ions in here. So I've got an acid solution in here and I've got hydrogen gas, and this is a possible half equation that's occurring. So I've got hydrogen ions grabbing an electron and turning into hydrogen gas. Now for example on this side it might be zinc. We've been using zinc a lot. Let's assume this is zinc and we've got some zinc ions in here. In this particular instance, the electrons in the actual zinc metal are more attracted towards the hydrogen ions in this solution than they are to the zinc ions which constitute the metal lattice. What does that mean? That means that the zinc donates electrons, and electrons start travelling through here and into this half cell, so that the hydrogen ions from the acid in the solution grab an electron and turn into hydrogen gas. So I actually get extra hydrogen gas being produced on this side. The standard hydrogen electrode is just used as a reference for different types of half cells. So this, we used an example of zinc here, and we got what's called an electrode potential, which is indicated by the E with a superscript 0. These, I'm just going to call them E0 values. The E0 values can be used to work out the overall voltage that a cell produces. And it works out that the more reactive a metal is, the more likely it will donate electrons towards the hydrogen, ions in this case. But if we have a less reactive metal, for example silver, then the opposite occurs. Now in this case, instead of having zinc as this electrode, if we had a silver a solid silver electrode. And the solid silver, well, silver is a much more stable metal, much less reactive metal, and silver ions will tend to steal electrons away from hydrogen gas and turn themselves into silver atoms. So what happens is, if I have a silver ion in this solution, it'll bump against my silver electrode and it'll actually pull electrons away from hydrogen gas that's bubbling through here and bubbling against this inert electrode, and we get this reaction occurring, this oxidation. So the hydrogen gas is oxidized to produce hydrogen ions plus an electron. Now those electrons flow through the external circuit into here, and a silver ion becomes a silver atom. So this electrode will actually get thicker with silver. It'll get a thicker thicker plating of silver on top of the existing silver, and what's happening here is the hydrogen gas is turning into hydrogen ions, and this solution will actually get more acidic as more hydrogen ions are produced. This is the table of standard reduction potentials. Now this is included in the HSC. It's on the reverse side of the periodic table, and it tells you what voltage is present when you've got different metals, different half cells hooked up to hydrogen. So this is the equation for the hydrogen standard electrode. So say for example, if I had the other electrode is a lead ions, so a lead electrode into some lead ions, so for example lead nitrate, I'd get a voltage of minus 0.13. What that minus means is that this reaction doesn't occur as is, it's reversed. So it would be written as lead going to give lead ions and electrons. It means that the hydrogen ions get the electrons. So these voltages are compared to the standard hydrogen electrode. So if it is negative, so for example if I've got a zinc electrode hooked up to a standard hydrogen electrode, well, the zinc is minus 0.76. That means this equation does not happen as written, it happens in the reverse direction. It means that the zinc metal is donating electrons to the hydrogen ions to produce hydrogen gas. Now these values can be used to calculate the potential voltage of any combination of half cells. For example, if I've got a zinc half cell, so I'd have a zinc electrode and some zinc ions, I've got a copper electrode and some copper ions. Now once again the chemicals in these just pretty much mirror the actual equation. So I've got zinc metal in zinc ions, I've got copper metal in some copper ions. Now in this case the zinc donates electrons to the copper. How do I work that out? I work it out by looking at the table of standard reduction potentials. Copper is lower down on the list. Now I'm looking at copper 2 plus here, not the copper 1 plus, because I've got copper sulfate, so USO4, so it's copper 2. Now copper is lower down than zinc. Now the more positive the value, or the lower down on the table, that is the one that is going to get the electrons, that is the one that is going to be reduced. So because this one is lower down, I know that copper ions are going to be reduced and the zinc is going to be oxidized. So that one will be written in the opposite direction, because the zinc is being oxidized to give zinc ions and electrons. Where are those electrons going? They're going into the copper ions, which are reduced to give copper. Now these are the half equations as written. These are because we're talking about a table of standard reduction potentials. So this is the cell potential for the reduction of zinc. We get a minus 0.76. Well, because copper is more positive, it's less reactive, it will tend to grab the electrons So the copper ions are going to be reduced and the zinc metal is going to be oxidized. So I've just gotten that particular equation, I have flipped it. So that the zinc solid is being oxidized to give zinc ions and electrons. And you'll need to note that the negative sign is reversed. When you flip the equation, you flip the charge, the electrode potential. So now I've got zinc being oxidized, I've got copper ions being reduced. The electrode potential for the zinc being oxidized is 0.76. The electrode potential for the copper ions being reduced, 0.34. You just add those together. So theoretically, that particular galvanic cell will produce a voltage of 1.1 volts. Now let's put these together. We've got our zinc being oxidized, we've got our copper ions being reduced. What I'm going to do is grab everything on this side of the equation and put them on. Grabbing that, and I'm just putting them over here. In the same way, get everything on this side of the equation and I put that over here. So I've got my solid zinc plus my copper ions plus 2 electrons, going to give zinc ions plus 2 electrons plus solid copper. Now I've got two things here that we can cross off. We've got electrons on both sides, just cross those off, and that leaves us with a net ionic equation for this particular reaction. So once again I've got zinc plus copper ions going to give zinc ions plus copper. So effectively what's happening are 2 electrons are going from the zinc, solid zinc, into a copper ion. They just happen to be doing that through an external circuit. And the zinc turns into zinc ions, the copper ions turn into solid copper. Now an example of that written as a complete equation, we've got zinc plus copper sulfate going to give zinc sulfate plus copper. And in this case, the sulfate ions are spectators, and that's why they're not included in the net ionic equation. Here is another example of a galvanic cell. This one's a little bit different in that we have an inert platinum electrode. We've got Fe2 plus and Fe3 plus ions in solution. So this is mostly water with Fe2 plus and Fe3 plus ions floating around in it, plus whatever spectator ions were put there. So there might be nitrates or sulfates, whatever these were actually bonded to when they were a solid. My other electrode is magnesium in this case, in magnesium ion solution. Now for this one, first off, magnesium is up here. So we know that's fairly reactive, so the chances are that the magnesium is going to be oxidized to give magnesium ion, so that reaction will be actually written in the reverse direction. Now in this case we need to look for iron. So this iron here, look, that goes to Fe solid. We do not have Fe solid in our solution there. What we have, and even our electrode is an inert platinum electrode. What we actually have is Fe3 plus and Fe2 plus. Now in this case, the Fe3 plus is going to grab an electron and turn into Fe2 plus. Now that's got a voltage of a standard electrode potential of 0.77 volts. So I've got magnesium minus 2.36, I've got iron 3 plus going to iron 2 plus 0.77 volts. So this reaction is the one that will happen in this direction, so that will be on my reduction and this will be my oxidation. So here we go, we've got the equations, we've got Fe3 plus an electron going to give Fe2 plus. This is as written, this is just copied straight from the table of standard reduction potentials. The magnesium is written as an oxidation, it's 2.36 volts. I've changed the sign. Again, these are written, all of them are written as reductions. In this case it is oxidized, my sign changes. Add those two together and I get 3.13 volts. Let's put these together. Now the interesting thing about putting this together, I've got 1 electron here, I've got 2 electrons there. So what I have to do, when I'm putting these equations together, these half reactions together to make up my full equation, I have to balance the number of electrons. So Fe3+, well I need 2 Fe3+, plus 2 electrons, going to give 2 Fe2+. And why do I need that? I need 2 electrons here to balance these 2 electrons. So once again, I get everything on one side of the arrows and put them together. I get everything on the other side of the arrow and I put those all together. Now once again, I've got iron 3+, going to give iron 2+. I've got magnesium solid being oxidized to magnesium ions, and I've got 2 electrons on this side and 2 electrons on that side. So my overall equation is Fe3+ plus solid magnesium, going to give Fe2+ plus magnesium ions. Now this is the net ionic equation. I'm totally ignoring spectator ions, which could be nitrate, they could be anything that is soluble, a soluble salt of iron 2+ and iron 3+.